This project uses a rotary encoder to increase or decrease the hexadecimal count on a 7-segment display. The count can be reset by pressing the center of the encoder's dial. The original version of this project involves incrementing the count on the display via a push button and resetting the count via another push button. However, this video showcases the enhanced version with the rotary encoder. This project is built upon the Dolgan Development Platform version 6, designed by Jay Dolgan and updated by C. Darcy. The DDB V6 is a development board centered around the 14-pin ATtiny84 microcontroller. The board allows for easy programming of the MCU and for its GPIO pins to be used with external components. Code can be uploaded to the board via a header on the side and a SparkFun AVR Pocket programmer. The board can be powered via the programmer, a DC jack with a 5-volt regulator, or mini USB port. The board also offers an onboard LED and serial support via a USB to serial cable. The PCB is housed in a custom 3D printed case and secured to the case via screws. This project consists of 3 subcircuits. The first subcircuit is the input circuit, consisting of the rotary encoder connected to port A bits 0 and 1 of the MCU. The button on the dial of the rotary encoder is connected directly to the reset pin of the MCU. When the dial is turned clockwise, the count increases. When it is turned counterclockwise, it decreases. A rotary encoder has 2 output pins, A and B, both pulled up to high via resistors. Within the encoder, there is a grounded plate with discs that spins as the dial is turned, grounding the pins as it comes in contact with them. This produces a digital signal on the output pins depending on the direction turned. By reading the state of these pins, the direction of rotation can be determined. When A changes state, it is read and recorded. If the new state of B is the same as the previous state of A, the encoder has been turned counterclockwise. If the new state of B is different than the previous state of A, the encoder has been turned clockwise. The second subcircuit is the processing circuit, consisting of the ATtiny84 on the DDB V6. The third and final subcircuit is the output circuit, which consists of an SN74HC595N shift register connected to the MCU via its data, latch, and clock pins and the first 7 inputs of the common cathode 7-segment display. Segment map data for each hexadecimal digit is shifted out to the shift register, turning on the correct segments and illuminating the given digit. Segment map data is stored in a custom library for the DDB V6. This library also contains a custom register-level shift-out function that has predefined MCU pins as per the ideal pins for SPI communication. The code for this project uses pin change interrupts. Each GPIO pin of the ATtiny84 can be used as a pin change interrupt pin. In this case, port A is used for pin change interrupts, and it is activated by toggling the PCIe 0-bit high in the general interrupt mask register. The 2 bits used for interrupts, port A bit 0 and 1, are then activated by toggling their respective bits high in the pin change mask register. When any activated pin undergoes a change on port A, the PCIF 0 bit in the general interrupt flag register goes high, and a specific ISR corresponding to port A, PCN0_vect, is executed. When the ISR is triggered, a triggered variable is set to true, and then the current state of the A pin on the rotary encoder is recorded. In the loop, the triggered variable is checked and then set to false if it's true. Then, if A has changed state, it is compared against the current value of B as described before, and the count is increased or decreased accordingly. If it is greater than 15, it is rolled back to 0. Finally, the state of A is recorded again, and the value is shifted out using the custom shift out function in the library.